In 1977, humanity threw a bottle into the cosmic ocean. That bottle is still traveling, and what it found at the edge of everything we call home has left the scientists tracking it genuinely, quietly, and in some cases, permanently unsettled. The models were wrong. The boundary was not what we thought. And the universe waiting on the other side of our solar system is stranger, colder, and more hostile than any textbook prepared us for. This is what they found. And this is why it matters more than almost anything else happening on the planet you are currently sitting on. What Voyager 2 actually is to understand why what Voyager 2 discovered is so disturbing. You first need to understand what Voyager 2 actually is, because most people, if they are honest, have a vague idea. Something NASA launched, something that went to Jupiter maybe, something with a golden record that Carl Sagan was excited about. And that is roughly correct, but it misses the point almost entirely. Voyager 2 is a machine the size of a small car. It weighs about 825 kilograms. It was built in the early 1970s by engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, working with slide rules and computers that had less processing power than the phone in your pocket. Less power, honestly, than most modern toasters. And these people, armed with those tools, designed a spacecraft that is still functioning nearly 50 years after launch. Let that sink in for a moment. You probably cannot find a household appliance from 1977 that still works. Voyager 2 does. It launched on August 20th, 1977, 16 days before its twin, Voyager 1, which launched on September 5th of the same year. The reason Voyager 2 launched first, despite having a lower number, is that it was sent on a slower, longer trajectory. Voyager 1 got the faster path. Voyager 2 got the scenic route. And that scenic route would turn out to be one of the most scientifically productive journeys in human history. The spacecraft carries 11 scientific instruments, including magnetometers to measure magnetic fields, plasma detectors, cosmic ray sensors, and ultraviolet spectrometers. It carries a radioisotope thermoelectric generator, a device that converts heat from decaying plutonium into electricity. No solar panels. Out past Jupiter, sunlight is so weak that solar panels become essentially decorative. The plutonium does the work, and it carries something else. Mounted on its body is a 12-inch gold-plated copper disc, the famous golden record. It contains sounds and images from Earth, greetings in 55 languages, music ranging from Bach to Chuck Berry, the sound of rain, surf, and a mother's first words to a newborn child, instructions for how to play it encoded in binary, on the assumption that whatever finds it will be smart enough to figure that out, but will not already own a record player. Nobody has found it yet. As far as we know, the Grand Tour, a once-in-179-year opportunity. Here's the thing about Voyager 2's mission that most people do not fully appreciate. The entire project was only possible because of a planetary alignment that occurs once every 179 years. In the late 1960s, a young NASA mathematician named Gary Flandreau was working on a graduate project at JPL. He was calculating spacecraft trajectories when he noticed something extraordinary. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune would all be aligned on the same side of the Sun in a configuration that would not repeat until the year 2154. If you launched a spacecraft at exactly the right time, you could use each planet's gravity as a slingshot, swinging the craft toward the next target and accelerating it along the way without burning any additional fuel, a technique called gravity assist. Flandreau called it the Grand Tour. NASA almost did not do it. Budget cuts in the early 1970s scaled the original Grand Tour mission down dramatically. The full 4-planet mission was considered too expensive, but a stripped-down version survived, and the trajectory was designed so that if NASA chose to extend the mission after Saturn, the option would still be available. They chose to extend it. Voyager 2 became the only spacecraft in history to visit all 4 outer planets. At Jupiter in 1979, it discovered active volcanoes on the Moon Io, the first time volcanic activity had been confirmed anywhere other than Earth. At Saturn in 1981, it provided stunning close-up imagery of the ring system and discovered new details about the moon Titan. At Uranus in 1986, it found 10 previously unknown moons and revealed that the planet rotates on its side, essentially rolling around the sun like a bowling ball. At Neptune in 1989, it discovered that the largest moon Triton orbits in the wrong direction and is slowly spiraling toward the planet in a collision course that will play out in approximately 3.6 billion years. Then the planets ran out, and Voyager 2 kept going, the long silence and the journey. Outward after Neptune, there were no more targets, no more slingshots, no more close flybys with dramatic imagery and press conferences and front-page photographs. There was just the void. For the next 2 decades, Voyager 2 traveled outward through the outer solar system, a region called the heliosphere. This is the vast bubble of charged particles and magnetic fields that the sun continuously blows outward in all directions through what is called the solar wind. The heliosphere is enormous, extending tens of billions of kilometers from the sun in every direction. It is, in a very real sense, the sun's sphere of influence, the region where the sun's output still dominates the surrounding environment. Voyager 2 drifted through this region at roughly 55,000 kilometers per hour, which sounds fast until you realize how much empty space it was crossing. The distances involved in interstellar travel break human intuition completely. Light, the fastest thing in the universe, takes about 8 minutes to travel from the sun to Earth. It takes light over 4 hours to reach Neptune, and the edge of the heliosphere is roughly 3 times farther than Neptune. During those quiet decades, the spacecraft's instruments kept recording. Scientists back on Earth kept listening. The data that came back was not dramatic. Particle counts, magnetic field readings, plasma density measurements, the deep, patient data collection of a machine doing its job in the dark with no audience and no applause. Some of the original mission team members retired. Some died. A new generation of scientists took over the tracking. Children who had watched Voyager's Neptune flyby on the news grew up to become the people responsible for monitoring the signal. And the signal was getting weaker, and the distance between question and answer was growing. By the time Voyager 2 approached the edge of the heliosphere, a radio signal sent from Earth took over 16 hours to reach it. 16 hours. You could sleep, wake up, eat breakfast, go to work, come home, and the signal would still not have arrived. The heliopause, where the sun lets go. The edge of the heliosphere has a name. It is called the heliopause, and before Voyager 2 crossed it, we understood it mostly in theory. Here is what the theory said. The sun constantly emits the solar wind, a stream of charged particles flowing outward in all directions at hundreds of kilometers per second. As this wind travels outward, it eventually encounters the interstellar medium, the thin gas and particles that fill the space between star systems. At some point, the pressure of the solar wind is exactly balanced by the pressure of interstellar space. That boundary is the heliopause. Cross it in one direction and you are leaving the sun's influence. Cross it in the other direction and you are entering it. Before any spacecraft had actually been there, scientists built models of what the heliopause should look like. They expected a relatively clean boundary, a somewhat abrupt transition from solar wind to interstellar medium. They expected the magnetic field to shift in a predictable way. They expected the temperature and density of the plasma to change in patterns that matched their equations. They had never been there. They were essentially guessing, educated, mathematically rigorous, peer-reviewed guessing, but guessing nonetheless. Voyager 1 crossed the heliopause first, in August 2012, becoming the first human-made object to enter interstellar space. The data it sent back was fascinating but incomplete. Its plasma instrument had stopped working in 1980, leaving a significant gap in what it could measure. Scientists confirmed the crossing happened, but some questions remained open. Then Voyager 2 crossed the heliopause on November 5th, 2018, and it had a working plasma instrument, and that is where things got complicated. What Voyager 2 actually found when it crossed over. When Voyager 2 crossed the heliopause, the scientific team at JPL expected surprises. What they did not expect was how wrong their models actually were. 4 anomalies hit them immediately. First, temperature. The interstellar plasma was 45,000 to 50,000 degrees Celsius colder than predicted. Not a rounding error, a fundamental gap in how scientists understood energy behavior at this boundary. Second, density. Instead of a thin transition zone, Voyager 2 found a wall of compressed plasma piling up where solar wind meets interstellar space. 4.5 billion years of buildup. Nobody had that in the equations. Third, the magnetic field rotated faster and cleaner than expected. Not a fuzzy gradient. A genuine, defined edge, like a door, not a curtain. Fourth, cosmic rays. The moment Voyager 2 crossed over, the count spiked dramatically. The sun had been blocking them all along. We just never knew how much until we stepped outside and looked back. 5 separate papers published simultaneously in Nature Astronomy in November 2019 all contained some version of the same phrase. Not predicted by current models. 5 papers. Same admission. Scientists hate saying that, which means they absolutely meant it. The signal anomaly nobody can explain. Now here's the part of the story that does not get told in most coverage of Voyager 2, because most coverage focuses on the science, the boundary crossing, the historic milestone, what the instruments found. What most coverage skips is the moment in 2020 when NASA engineers sent a routine command to Voyager 2 and something went wrong. In January 2020, a sequence of commands was sent to the spacecraft to rotate its onboard instruments for a calibration test. This is a standard procedure performed regularly throughout the mission. Nothing unusual about the command itself. But something went wrong in the execution. 2 systems on board that are not supposed to operate simultaneously ended up running at the same time, drawing more power than the spacecraft's aging generator could comfortably provide. The spacecraft automatically responded by shutting down scientific instruments to protect itself. This is expected behavior, a built-in safety mechanism, but the shutdown knocked the spacecraft into a fault protection mode and severed contact with Earth. For approximately 5 months, Voyager 2 went dark. Think about what that means. The farthest human-made object in history, a spacecraft that had been continuously communicating with Earth since 1977. The only probe we have ever sent that successfully crossed the heliopause with a functioning plasma instrument. Gone silent in interstellar space, with a round-trip communication delay of over 30 hours. If you sent a distress signal from Voyager 2, Earth would not receive it for over 16 hours. Earth's response would take another 16 hours to arrive. Anything that needed immediate intervention was, by definition, already over by the time anyone on Earth knew about it. Scientists spent those months carefully diagnosing the problem from an impossible distance, reconstructing what had happened based on the last data received before contact was lost, designing commands to slowly bring the spacecraft back to a stable operating state, and then waiting hour after hour for responses that took the better part of a day to arrive. They got it back. In October 2020, Voyager 2 reestablished contact and resumed normal operations. But for a mission team that had spent decades nursing this spacecraft across the solar system, those months were not something anyone who lived through them describes casually. The closest analogy is probably waiting for a family member to come out of surgery, except the surgery is happening 12 billion kilometers away, and your pager takes 16 hours to receive updates. What this tells us about interstellar space. Here is what Voyager 2's crossing of the heliopause tells us about interstellar space that we did not know before. And some of it is deeply strange. The interstellar medium, the stuff between the stars, is not empty. This is something scientists knew in theory, but that Voyager 2 measured directly for the first time with a functioning plasma instrument. The space between star systems is filled with a thin plasma of ionized hydrogen and helium threaded through with magnetic fields carrying cosmic rays from violent events across the galaxy and maintaining a pressure that physically holds back the bubble of our solar system from expanding further. It is not a vacuum. It is more like an extremely thin, extremely cold, extremely hostile ocean. And our solar system is a bubble floating in it. What Voyager 2 revealed is that this ocean pushes back harder than expected. The boundary between solar wind and interstellar medium is sharper, denser, and more energetically complex than the models captured. The heliosphere is not a smooth, symmetrical bubble. Voyager 1 crossed the heliopause at a different distance from the Sun than Voyager 2 did, suggesting the bubble is asymmetrical, squashed on one side where it faces the direction of the solar system's movement through the galaxy. Our solar system is not sitting still. It is moving through the galaxy at approximately 828,000 kilometers per hour. As it moves, it pushes against the interstellar medium, creating a kind of bow shock on the leading edge and a long tail on the trailing edge, like a comet. Except the comet is everything we have ever known. The data from Voyager 2 suggests the nose of this structure, the leading edge facing into the galaxy's wind, is compressed and energetically active in ways that will take years of continued analysis to fully understand. We are not floating peacefully in space. We are plowing through it. And what we are plowing through is more complex than we realized. The pale blue dot problem. On February 14th, 1990, when Voyager 1 was approximately 6 billion kilometers from Earth, NASA instructed it to turn its camera back toward the sun and take a photograph. The resulting image showed Earth as a tiny point of light, less than a pixel wide, suspended in a beam of scattered sunlight. Carl Sagan called it the pale blue dot. He wrote about it in a passage that has since become one of the most quoted reflections on human existence ever put to paper. The gist of it, stripped of Sagan's extraordinary prose, which I will not reproduce here because it belongs to him, and I genuinely cannot do it justice, is this. From 6 billion kilometers away, every king, every war, every moment of glory and cruelty in human history fits on a mote of dust suspended in a sunbeam. Voyager 2 is now more than twice as far from Earth as Voyager 1 was when that photograph was taken. It is beyond the reach of the sun's wind. It is in interstellar space. If it turned its camera back toward the sun right now, our star would look like any other star in the sky. Bright, certainly, but just a star. There is something about that fact that is very difficult to fully absorb. The spacecraft took 41 years to get there. It used the gravity of 4 planets to accelerate. It survived equipment failures and power shortages and the death of the engineers who built it. And it crossed a boundary that, for billions of years before human beings existed to notice it, had simply been the unremarked edge of a star's influence in an unremarkable corner of the galaxy. We built something that crossed that boundary. With slide rules and plutonium and the scientific equivalent of a really long string, we reached interstellar space. And then we measured it. And then we found out we were wrong about what was there. That is either the most humbling thing our species has ever done or the most impressive, depending on your mood. Probably both. Why scientists are genuinely disturbed here is what genuinely disturbs the scientists who work with Voyager 2's data. And I want to be precise about this because disturbed is a strong word and I do not want to oversell it. Nobody is lying awake at night screaming, but there is a specific kind of scientific unease that comes from a particular situation. The models were wrong, not catastrophically, not in ways that overturn fundamental physics, but wrong in measurable, significant, documented ways. The temperature anomaly was real. The plasma density wall was real. The cosmic ray jump was sharper than expected. The asymmetry of the heliosphere was confirmed. Each of those findings means that the mathematical frameworks scientists had been using to describe the boundary of our solar system were missing something. Something physical was happening there that the equations did not capture. And the only way to know that something was missing was to go there. 41 years of travel just to discover that the textbooks were incomplete. But here is the part that keeps the more philosophically minded researchers up at night. We have two data points, Voyager 1 and Voyager 2. They crossed the heliopause at different distances from the sun, on different sides, in different years. That is it. Two crossings, two locations, two snapshots of the most significant boundary in our cosmic neighborhood. The heliosphere is enormous. The heliopause extends in every direction for tens of billions of kilometers. And we have sampled it in exactly two places, using two spacecraft, launched on the same day in 1977, with technology designed over 50 years ago. Every conclusion we are drawing about the nature of the heliopause, the structure of the interstellar medium, the asymmetry of the heliosphere, every one of those conclusions is based on data from 2 points in an immeasurable boundary. If you wanted to understand the coastline of an entire continent, sampling 2 locations would give you the most tentative, hedged, preliminary conclusions imaginable. But that is where we are. The models were built on theory. Now we have data, and the data does not fully match the theory, which means either the theory needs revision or the 2 data points we have are not representative of the full boundary. Both possibilities have significant implications. And we currently have no way to find out which one is true. What happens next and why, that is terrifying. Voyager 2 is dying. This is not a metaphor, and it is not dramatic language. It is an engineering fact. The radioisotope thermoelectric generator that powers the spacecraft loses roughly 4 watts of power per year as the plutonium decays. When Voyager 2 launched in 1977, it had about 470 watts of power available. Today it has less than half that. The mission team has been managing this decline for decades, turning off instruments and heaters one by one to concentrate remaining power on the most critical systems. In 2020, to compensate for power shortages, NASA engineers turned off one of the 5 remaining scientific instruments on Voyager 2, the plasma science instrument that had been so crucial to the heliopause crossing. That is the instrument that made Voyager 2's crossing historically unique. It is now off. The data it collected during the crossing has been preserved, but the instrument that collected it is no longer operating. The remaining 4 instruments are measuring cosmic rays, magnetic fields, low-energy charged particles, and plasma waves. They are expected to remain operational until approximately 2026, give or take a few years depending on how the team manages power consumption. After that, one by one, they will go dark. When the last instrument goes off, Voyager 2 will still be traveling. It will cross paths with the Oort cloud, the distant shell of icy objects that surrounds our solar system, in roughly 300 years. In approximately 40,000 years, it will pass within 1.5 light years of a star called Ross 248. It will carry its golden record, its names, its sounds, its message, from a species that no longer exists in its current form, silently through interstellar space for billions of years. We will hear nothing from it after the instruments die. We will have no way to know what it passes. We will have no way to know if anyone finds it. And we may not send another probe to the heliopause for decades. The proposed interstellar probe mission, a concept NASA has been studying, would launch no earlier than the 2030s. And would take decades to reach the heliopause, even with modern propulsion. The data gap between Voyager 2 going silent and the next probe reaching interstellar space could be 50 years or more, 50 years of blindness. at the most interesting boundary we have ever discovered. So here is what all of this means. Not the technical version, the real version. For the entirety of human history until November 5th, 2018, every human being who ever lived, every philosopher, every astronomer, every person who ever looked up at the night sky and wondered what was out there, all of them lived inside the heliosphere, inside the sun's bubble, inside the invisible protective boundary that shields us from the full force of the interstellar medium. Not one human had ever been outside it. Not one instrument had ever crossed it with a full set of working sensors and reported back what was on the other side. On November 5th, 2018, Voyager 2 crossed that line. And what it found was that the boundary is sharper than we thought and thicker in some ways, that the universe outside is colder and more energetically complex than our models predicted, that the cosmic rays flooding interstellar space are more intense than the shielded environment inside the heliosphere suggested, that the sun has been protecting this small collection of planets from a genuinely hostile environment for 4.5 billion years, and we had not fully appreciated how much work that protection was doing. The real discovery of Voyager 2 is not a specific number or a specific anomaly. The real discovery is the shape of our ignorance. For decades, we built mathematical models of the heliopause and believed they were substantially correct. Voyager 2 showed us where they were wrong, and every place a model is wrong is a place where something real is happening that we do not yet understand. Jeremy Wade spent 9 seasons filming rivers and came home to say the real monster was us and our refusal to look clearly at what we were losing. The scoop marks in Aswan have been sitting in plain sight for over a century while we insisted they must fit the tools we already knew about. The Dead Sea Scrolls sat in caves for 2,000 years, keeping a secret about diversity and origin that only a completely different scientific discipline could finally unlock. Voyager 2 spent 41 years crossing the solar system and crossed a boundary we had theorized about for generations. And when it got there, it told us the theory was incomplete. This is the pattern. This is what science keeps discovering. Not that we know nothing, but that the boundaries of what we know are hazier and stranger than we assumed, and that the most important discoveries are almost always waiting right at the edge of the maps we have already drawn. Voyager 2 is out there right now, 12 billion kilometers from the sun, moving through interstellar space at 55,000 kilometers per hour, slowly dying, still transmitting, still measuring, still sending back data that scientists are still analyzing. It will outlast the civilization that built it. The golden record it carries will survive longer than human language. The atoms that make up its structure were forged in the cores of stars that exploded billions of years before our sun formed. And it is telling us in the clearest possible terms that the universe is larger and stranger and more complicated than our models predicted. That the edge of everything we call home is not the peaceful, well-understood boundary we thought it was. That interstellar space is not empty. That the sun's protection is not guaranteed. That we are a small, warm, shielded island in an ocean we have barely begun to measure. We sent a message in a bottle into the cosmic ocean in 1977. The bottle crossed the ocean's edge in 2018. And the message it sent back to us is this: you were right to wonder, you were wrong about the details. And there is so much more out there than you know. That is why Voyager 2 matters. Not the milestone, not the press release, not the anniversary coverage. The fact that a machine built with slide rules and plutonium went somewhere no human instrument had ever gone and came back with data that made the people who dedicated their careers to understanding that place say quietly to each other that we need to rethink this. That is the story. That is always the story. And we are nowhere near done telling it.